Nuclear weapons delivery is the technology and systems used to place a nuclear weapon at the position of detonation, on or near its target. Several methods have been developed to carry out this task. Strategic nuclear weapons are used primarily as part of a doctrine of deterrence by threatening large targets, such as cities. Weapons meant for use in limited military maneuvers, such as destroying specific military, communications, or infrastructure targets, are known as tactical nuclear weapons. In terms of explosive yields, nowadays the former have much larger yield than the latter, even though it is not a rule. The bombs that destroyed Hiroshima and Nagasaki in 1945 were weaker than many of today's tactical weapons, yet they achieved the desired effect when used strategically. Nuclear triad. A nuclear triad refers to a strategic nuclear arsenal which consists of three components: traditionally strategic bombers, intercontinental ballistic missiles, and submarine-launched ballistic missiles. The purpose of having a three-branched nuclear capability is to significantly reduce the possibility that an enemy could destroy all of a nation's nuclear forces in a first-strike attack. This, in turn, ensures a credible threat of a second strike, and thus increases a nation's nuclear deterrence. Main delivery mechanisms. Gravity bomb equals. Historically, the first method of delivery, and the method used in the only two nuclear weapons actually used in warfare, was a gravity bomb dropped by a bomber. In the years leading up to the development and deployment of nuclear-armed missiles, nuclear bombs represented the most practical means of nuclear weapons delivery. Even today, and especially with the decommissioning of nuclear missiles, aerial bombing remains the primary means of offensive nuclear weapons delivery, and the majority of U.S. nuclear warheads are represented in bombs, although some are in the form of missiles. Gravity bombs are designed to be dropped from planes, which requires that the weapon be able to withstand vibrations and changes in air temperature and pressure during the course of a flight. Early weapons often had a removable core for safety, known as in-flight insertion cores, being inserted or assembled by the aircrew during flight. They had to meet safety conditions, to prevent accidental detonation or dropping. A variety of types also had to have a fuse to initiate detonation. U.S. nuclear weapons that met these criteria are designated by the letter B followed, without a hyphen, by the sequential number of the physics package it contains. The B-61, for example, was the primary bomb in the U.S. arsenal for decades. Various air-dropping techniques exist, including toss bombing, parachute-retarded delivery, and laydown modes, intended to give the dropping aircraft time to escape the ensuing blast. The early gravity nuclear bombs could only be carried by the B-29 Superfortress. The next generation of weapons were still so big and heavy that they could only be carried by bombers such as the B-52 Stratofortress and V-bombers, but by the mid-1950s smaller weapons had been developed that could be carried and deployed by fighter bombers. Ballistic missile equals. Missiles using a ballistic trajectory usually deliver a warhead over the horizon, at distances of thousands of kilometers, as in the case of intercontinental ballistic missiles and submarine-launched ballistic missiles. Most ballistic missiles exit the Earth's atmosphere and re-enter it in their suborbital spaceflight. Placement of nuclear missiles on the low Earth orbit has been banned by the Outer Space Treaty as early as 1967. Also, the eventual Soviet fractional orbital bombardment system that served a similar purpose it was just deliberately designed to deorbit before completing a full circle was phased out in January 1983 in compliance with the SALT II treaty. An ICBM is more than 20 times as fast as a bomber and more than 10 times as fast as a fighter plane, and also flying at a much higher altitude, and therefore more difficult to defend against. ICBMs can also be fired quickly in the event of a surprise attack. Early ballistic missiles carried a single warhead, often of megaton range yield. Because of the limited accuracy of the missiles, this kind of high yield was considered necessary in order to ensure a particular target's destruction. Since the 1970s, modern ballistic weapons have seen the development of far more accurate targeting technologies, particularly due to improvements in inertial guidance systems. This set the stage for smaller warheads in the hundreds of kilotons range yield, and consequently for ICBMs having multiple independently targetable re-entry vehicles. Advances in technology have enabled a single missile to launch a payload containing several warheads. The number of independent warheads capable of deployment from ballistic missiles depends on the weapons platform the missile is launched from. For example, one D-5 Trident missile carried by an Ohio-class submarine is capable of launching 8 independent warheads, while a Typhoon has missiles capable of deploying 10 warheads at a time. MIRV has a number of advantages over a missile with a single warhead. With small additional costs, it allows a single missile to strike multiple targets, or to inflict maximum damage on a single target by attacking it with multiple warheads. It makes anti-ballistic missile defense even more difficult, and even less economically viable, than before. Missile warheads in the American arsenal are indicated by the letter W. For example, the W-61 missile warhead would have the same physics package as the B-61 gravity bomb described above, but it would have different environmental requirements, and different safety requirements since it would not be crew-tended after launch and remain atop a missile for a great length of time. Cruise missile equals. A cruise missile is a jet engine or rocket-propelled missile that flies at low altitude using an automated guidance system to make them harder to detect or intercept. Cruise missiles can carry a nuclear warhead. They have a shorter range and smaller payloads than ballistic missiles, so their warheads are smaller and less powerful. The AGM-86ALCM is the U.S. Air Force's current nuclear-armed air-launched cruise missile. The ACM is only carried on the B-52 Stratofortress. This plane can carry 20 missiles. Thus the cruise missiles themselves can be compared with MIRV warheads. The BGM-UGM-109 Tomahawk submarine-launched cruise missile is capable of carrying nuclear warheads, but all nuclear warheads were removed. Cruise missiles may also be launched from mobile launchers on the ground, and from naval ships. There is no letter change in the U.S. arsenal to distinguish the warheads of cruise missiles from those for ballistic missiles. Cruise missiles, even with their lower payload, have a number of advantages over ballistic missiles for the purposes of delivering nuclear strikes. Launch of a cruise missile is difficult to detect early from satellites and other long-range means, contributing to a surprise factor of attack. That, coupled with the ability to actively maneuver in flight, allows for penetration of strategic anti-missile systems aimed at intercepting ballistic missiles on calculated trajectory of flight. Partially for those reasons, nuclear-armed cruise missiles are amongst the least deployed of all nuclear weapons, as their deployment is restricted by treaties such as SALT II. Other delivery systems Other delivery methods included artillery shells, mines such as the medium atomic demolition munition and the novel Blue Peacock, nuclear depth charges, and nuclear torpedoes. An atomic bazooka was also fielded, designed to be used against large formations of tanks. In the 1950s the U.S. developed small nuclear warheads for air defense use, such as the Nike Hercules. From the 1950s to the 1980s, the United States and Canada fielded a low-yield nuclear-tipped air-to-air rocket, the AIR-2 Genie. Further developments of this concept, some with much larger warheads, led to the early anti-ballistic missiles. The United States have largely taken nuclear air defense weapons out of service with the fall of the Soviet Union in the early 1990s. Russia updated its nuclear-tipped Soviet-era anti-ballistic missile, ABM, system, known as the A-135 anti-ballistic missile system in 1995. It is believed that the, in development, 2013, successor to the nuclear A-135, the A-235 Samolet M will dispense with nuclear interception warheads and instead rely on a conventional hit-to-kill capability to destroy its target. Small, two-man portable tactical weapons, such as the Special Atomic Demolition Munition, have been developed, although the difficulty to combine sufficient yield with portability limits their military utility. Costs. According to an audit by the Brookings Institution, between 1940 and 1996, the U.S. spent $8.78 trillion in present-day terms on nuclear weapons programs. 57% of which was spent on building delivery mechanisms for nuclear weapons. 6.3% of the total, $551 billion in present-day terms, was spent on weapon nuclear waste management, for example, cleaning up the Hanford site with environmental remediation, and 7% of the total, $617 billion was spent on the manufacturing of nuclear weapons themselves. Technology spin-offs equals. Strictly speaking, however, not all this 57% was spent solely on weapons programs delivery systems. Launch vehicles, for example, two such delivery mechanisms, the Atlas ICBM and Titan II, were repurposed as human launch vehicles for manned spaceflight. Both were used in the civilian Project Mercury and Project Gemini programs respectively, which are regarded as stepping stones in the evolution of U.S. manned spaceflight. The Atlas vehicle sent John Glenn, the first American into orbit. Similarly, in the Soviet Union, it was the U-7 ICBM launch vehicle that placed the first artificial satellite in space, Sputnik, on October 4, 1957, and the first human space flight in history was accomplished on a derivative of the U-7, the Vostok, on April 12, 1961, by cosmonaut Yuri Gagarin. A modernized version of the U-7 is still in use as the launch vehicle for the Russian Federation, in the form of the Soyuz spacecraft. Weather satellites. The first true weather satellite, the TIROS-1, was launched on the Thor-able launch vehicle April 1, 1960. The PGM-17 Thor was the first operational IRBM, intermediate ballistic missile, deployed by the U.S. Air Force. The Soviet Union's first fully operational weather satellite, the Meteor-1, was launched March 26, 1969 on the Vostok rocket, a derivative of the U-7 ICBM. Lubricants. WD-40 was first used by Convair to protect the outer skin, and more importantly, the paper-thin balloon tanks of the Atlas missile from rust and corrosion. These stainless steel fuel tanks were so thin that, when empty, they had to be kept inflated with nitrogen gas to prevent their collapse. Thermal isolation. In 1953, Dr. S. Donald Stuckey of the Corning Research and Development Division invented pyroceram, a white glass ceramic material capable of withstanding a thermal shock of up to 450 degrees Celsius. It evolved from materials originally developed for a U.S. ballistic missile program, and Stuckey's research involved heat-resistant material for nose cones. Satellite-assisted positioning. Precise navigation would enable United States submarines to get an accurate fix of their positions before they launched their SLBMs. This spurred development of triangulation methods that ultimately culminated in GPS. The motivation for having accurate launch position fixes, and missile velocities, is twofold. It results in a tighter target impact circular area probable and therefore by extension, reduces the need for the earlier generation of heavy multi-megaton nuclear warheads, such as the W-53, to ensure the target is destroyed. With increased target accuracy, a greater number of lighter, multi-kiloton range warheads can be packed on a given missile, giving a higher number of separate targets that can be hit per missile. Global positioning system equals. During a Labor Day weekend in 1973, a meeting of about 12 military officers at the Pentagon discussed the creation of a defense navigation satellite system. It was at this meeting that the real synthesis that became GPS was created. Later that year, the DNSS program was named Navstar, or Navigation System Using Timing and Ranging. During the development of the submarine-launched Polaris missile, a requirement to accurately know the submarine's location was needed to ensure a high circular area probable warhead target accuracy. This led the U.S. to develop the transit system. In 1959, ARPA also played a role in transit. The first satellite navigation system, Transit, used by the United States Navy, was first successfully tested in 1960. It used a constellation of 5 satellites and could provide a navigational fix approximately once per hour. In 1967, the U.S. Navy developed the detonation satellite that proved the ability to place accurate clocks in space, a technology required by the latter global positioning system. In the 1970s, the ground-based Omega navigation system, based on phase comparison of signal transmission from pairs of stations, became the first worldwide radio navigation system. Limitations of these systems drove the need for a more universal navigation solution with greater accuracy. While there were wide needs for accurate navigation in military and civilian sectors, almost none of those was seen as justification for the billions of dollars it would cost in research, development, deployment, and operation for a constellation of navigation satellites. During the Cold War arms race, the nuclear threat to the existence of the United States was the one need that did justify this cost in the view of the United States Congress. This deterrent effect is why GPS was funded. The nuclear triad consisted of the United States Navy's submarine-launched ballistic missiles along with United States Air Force strategic bombers and intercontinental ballistic missiles. Considered vital to the nuclear deterrence posture, accurate determination of the SLBM launch position was a force multiplier. Precise navigation would enable United States submarines to get an accurate fix of their positions before they launched their SLBMs. The USAF, with two-thirds of the nuclear triad, also had requirements for a more accurate and reliable navigation system. The Navy and Air Force were developing their own technologies in parallel to solve what was essentially the same problem. To increase the survivability of ICBMs, there was a proposal to use mobile launch platforms, and so the need to fix the launch position had similarity to the SLBM situation. In 1960, the Air Force proposed a radio navigation system called Mosaic that was essentially a 3D LORAN. A follow-on study, Project 57, was worked in 1963, and it was in this study that the GPS concept was born. That same year, the concept was pursued as Project 621B, which had many of the attributes that you now see in GPS, and promised increased accuracy for Air Force bombers as well as ICBMs. Updates from the Navy transit system were too slow for the high speeds of Air Force operation. The Navy Research Laboratory continued advancements with their detonation satellites, first launched in 1967, and with the third one in 1974 carrying the first atomic clock into orbit. Another important predecessor to GPS came from a different branch of the United States military. In 1964, the United States Army orbited its first sequential collation of range satellite used for geodetic surveying. The SECOA system included 3 ground-based transmitters from known locations that would send signals to the satellite transponder in orbit. A 4th ground-based station, at an undetermined position, could then use those signals to fix its location precisely. The last SECOA satellite was launched in 1969. Decades later, during the early years of GPS, civilian surveying became one of the first fields to make use of the new technology, because surveyors could reap benefits of signals from the less-than-complete GPS constellation years before it was declared operational. GPS can be thought of as an evolution of the SECOA system where the ground-based transmitters have been migrated into orbit. See also, History of nuclear weapons, List of nuclear weapons, Mutual Assured Destruction Doctrine, National Missile Defense of the United States, Nuclear Explosion, Nuclear Strategy, Nuclear Weapon Design, Nuclear Terrorism. Notes. References. Annotated bibliography for nuclear weapon delivery systems from the ALSO's Digital Library for Nuclear Issues. External links, Nuclear Missile Research Center.